Hi there. In this video, we're going to talk about the spread of the data, how spread out the data values are. Why is this relevant? Why does it matter? Well, imagine the following scenario. So somebody calls into the vet, and the vet asks, how much does they're calling about their dog, and the vet asks, how much does your dog weigh? And the person, maybe one person that calls in says, well, my dog weighs 8 pounds. All right, and then maybe the next call to the vet, somebody calls in and says, how much does your dog weigh? My dog weighs 195 pounds. Now, these values are very different, right? They're wildly different. And dogs have a range of weights from very tiny to like 5 pounds all the way to upward of 200 pounds, right? So wide variety of weights. So should the vet be concerned if somebody calls in and says, my dog weighs 180 pounds or my dog weighs only 8 pounds? No, the vet probably thinks, oh, it's probably just one of those dogs, right? Because there's such a wide variety of ranges of weights, we know that there's no reason to get excited if we find something particularly large or particularly small. Compare this to body temperature. If I call my doctor and tell her that I have a body temperature of, say, if I took my temperature and got 107, well, I think that's cause for great concern, right? That's a wildly high body temperature. Or if I called in and said my body temperature was 95, that might be very low, maybe 92, wow, like you got to do something, you're hypothermic, right? Now, the difference between 107 and 92 is only 15, right? Small difference especially compared to the difference in the dogs. But how do we know when to panic? How do we know when to be alarmed? Well, that's understanding the spread of the data. We understand that body temperatures for healthy adults don't spread very far. They're all concentrated right around, they say, 98.6 degrees, right? And they don't vary very much away from there. The spread of the data is very small. And so we know that if we get a value that's 15 points above average, that's reason for alarm. Whereas for dogs, the spread of the data is very big. So we don't get very alarmed if we see a particularly large value or a particularly small value. So the spread of the data tells us when a data value is extreme or not, whether we should be concerned. Okay? So let's talk about how to quantify the spread of data. How do we mathematically measure these things? So we're going to talk about two methods here. We're going to talk about IQR, interquartile range, and we talked about this in a previous video. And we're going to talk about standard deviation today. So let me just refresh your memory on what IQR is. And so the IQR is just the width of the box in a box plot. Right? So you make the box plot, as described in our last other video, and you just measure the width of the box. Or in other words, you take Q3 and subtract Q1. And that measurement is a good measurement about, on average, how spread out the data is. So that's one way to measure the spread of data. Okay? Another way to do it is to use what they call the standard deviation. The standard deviation comes in two forms. We have the population standard deviation and the sample standard deviation, just like we had the population mean and the sample mean. So the population standard deviation is given by this Greek letter sigma. This is the lowercase version of sigma. So sigma equals this quantity. All right? Instead of wording it out here, we'll go through an example and explain what all this means. We should recognize some of these symbols from when we were talking about mean. And we also have the sample standard deviation, which the formula looks almost identical, except that in the biggest difference here is that in the denominator, we have an n-1 instead of an n. Right? So we're going to subtract 1 in the sample standard deviation as opposed to the population standard deviation. Notice that the sample standard deviation is given the Latin letter S. Notice that the similar thing happened with the mean. Population mean was given a Greek letter, mu, and the sample mean was given a Latin letter, x bar. Here, the population standard deviation is given the Greek letter, sigma. The sample standard deviation is given the Latin letter, s. So this is a theme that runs throughout statistics. When we deal with population parameters, we use Greek letters. And when we talk about sample statistics, we use Latin letters. So what we're going to do is we're going to look at this data set here, and we're going to compute the standard deviation, assuming it's a population, and then assuming that it's a sample. Okay? So let's give this a shot. So here we are. So, compute the standard deviation assuming it's a population. So that means I'm going to be computing sigma. All right? So sigma, the formula is as follows. All right? Let's go ahead and compute this out. We got the square root. Right? Now, what is in the numerator? Well, the numerator is that Greek letter capital sigma. That means sum. This is the mathematical symbol for sum. So we're going to add up stuff. What are we adding up? We're adding up each data value minus the mean, and then we're going to square them. So we actually square them, and then we add them up. All right? So that means that to compute this, we need to compute the mean first. Okay? So what's the mean? Well, we talked about this in the last video. All right. We add up the data values and divide by the number that there are. Okay, let me just adjust my camera here. Okay, so so I got in the numerator I've got let's see, 12, and in the denominator I've got 4. So the mean is 3. Okay, so what I'm going to add up here is I'm going to take each data value, subtract the mean, and square it. And I'm going to do that for each data value, and I'm going to add them up. So I take the next one, subtract the mean, and then square it. The next one, next data value, subtract the mean, and square it. And then the last data value, subtract the mean, and then square it. And I see that I'm in the way here, sorry. Okay? And we're going to divide that by n. N is 4, the amount of data. Okay? So what do we get here? Well, if I simplify the numerator, 2 minus 3 squared, it's negative 1 squared, that's 1. 3 minus 3 squared is 0. 3 minus 3 squared is 0. 4 minus 3 squared is 1. So I end up with the square root of 2 over 4, or the square root of 1/2. Okay. What's the square root of 1/2? Let's just write it as a decimal. It's about 0.7071. So approximately 0.7071. And here we've computed the population standard deviation. We took each data value, we subtracted the mean, we squared that quantity, and then we added it up and then divide by the number, and we take the square root at the end. Okay? Let's try it again. Let's do the same thing, but we're going to assume the data was sample data. Okay? So the formula for sample standard deviation was as follows. It was given by S. It comes from a sample, so we use the Latin letter. It's the sum of each data value minus the mean. Now I'm using the sample mean, so I'm going to use x bar. And remember, the sample standard deviation, we divide by n minus 1 instead of n. Right? So here we go. What we need to do is we need to compute x bar. But remember, the formula for x bar is the same as the formula for mu. So if mu was 3, x bar is going to be 3 as well. Right? So we get the same thing. And so when we go to compute this, we're going to take each value. Let's go see what they were here. The first value was a 2, right? So I'm going to take 2. Oops. I'm going to take 2 minus the mean, square it. 3 minus the mean, square it. Let's scroll. Well, let's let me move myself here over to here. Woo. All right. I'm going to take the next value minus the mean, square it, and then the last value minus the mean and square it, right? And then we're going to divide by n minus 1, so 4 minus 1. So notice it's exactly the same thing we did above, except instead of dividing by 4, we're dividing by 4 minus 1. So when we simplify this, what we're going to get is, instead of square root of 2 divided by 4, we have 2 divided by 4 minus 1. That's 2 divided by 3 that we're taking the square root of. So that's approximately equal to 0.8165, about 0.8165. So the sample standard deviation ends up being a little bit different than the population standard deviation. Okay, so it's an involved formula. You got to do a number of mathematical, got to jump through a number of mathematical hoops here to get the answer, but this is how you do it. I'd like to take a moment to explain what this is doing. All right, so let's go off to the side here, and let's just talk about what we're doing here. What the standard deviation is measuring is it's measuring the average value that each number is away from the mean. So if you imagine a data set, so let me draw a number line, and then we have all our data points, okay? So suppose we've got a data point here, 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 here. We've got a bunch of data points, right? There they are. And we want to measure, on average, how far are they from the mean. That should give us an idea of how spread out they are. Okay, so what I do is I find the mean. Right? So maybe I identified that the mean was right there. Okay, so there's the mean. So what I'll do is, to find out how far the data values are from the mean, I'll just take the value of the data and subtract the mean. And that gives me a measurement of how far it is. And that's called the deviation. All right, so doing that is taking each data value and subtracting the mean. This is the mean here. And I want to average that. So I'm going to take those values. I want to know the average distance. So I want to know the average deviation. So I'm going to take those numbers and divide by let me use an n to represent the amount of data that we have. So you might naively think this is how we'd compute the standard deviation. It's the average distance things are from the mean. The problem is that this difference here, the x minus mu, will be positive when the data values are to the right of the mean, and it'll be negative when the data values are to the left of the mean. And so, on average, these are all going to cancel each other out. Some will be positive, some will be negative, so we should just generally get something close to 0 every time. And that's no good. That's not really giving us a good description of how spread out the data is if we're always getting something close to 0, right? So to avoid that, to avoid some of the values being positive and some of them being negative, what we do is we put a square here. So instead of just taking the difference, we square the difference. And then we take the average of those. But then you say, well, wait a minute, well, now we didn't really find the average of the deviations, we found the average of the square of the deviations. So we got something that's kind of been mathematically manipulated out of what we want it to be. So we have to undo the square. So what we do is when we're done, When we're done, we take the square root to undo the square. Right? So this is the motivation for where the formula comes from. Okay. All right, let's go back and see what else we can do see what else we learn about standard deviation. Looks like we have some more examples. Okay, so let's go ahead and take a look at these. Here we have two data sets. Which one has a larger standard deviation? Oops, you're not seeing what I'm seeing. Sorry about that. Okay, here we have two data sets. Which one has the larger standard deviation? Now, one person might naively say, well, the one on the left does, of course, right? Because look at how big those numbers are. But think about it. The standard deviation is the average amount that datas differ from the mean. So it's not how big the values are, it's how different they are from the mean. And if we look at the values on the left here, these values are all right around 145, right? They're all pretty close. They're all within 2 of 145, right? So they're all pretty close together. So that means that the standard deviation is actually quite small. So we'd expect sigma to be quite small here. In fact, if I were to estimate it, I would estimate it probably be around 1. On average, it looks like the mean's about 145 here. And it looks like some things are 2 units away, some things are 1 unit away, but on average maybe 1 or maybe just 1 unit away from 145, right, on average. So the sigma is quite small here. Now look at this data on the right. These numbers are small, but what would your guess be as to the mean here? We've got numbers ranging from 0 to 30, and they're pretty just evenly spaced as multiples of 5 here. I would guess that 15 is probably the mean, right? So how far are numbers from the mean? Well, we've got numbers that are quite a bit away from the mean. We got 30 is 15 away from the mean, and 0 is 15 away from the mean. On average, I would think that sigma here is probably, on average, something around, what's halfway between 15 and 30? Well, maybe like 7.5 or 7 or 8 or something like this. I would think the sigma is a little bit larger here. So notice that the size of the data values themselves doesn't actually tell you what the standard deviation is. The standard deviation is how varied the values are. And this goes back to kind of the example that I gave at the beginning with body temperature. Body temperatures are near 100, right? But the standard deviation is very small. We don't expect human body temperatures to vary that much, right? If you're alive, right? If you're alive, your body temperature is really close to 98.6. Right? Even though the number is quite big, the standard deviation is quite small, right? And the weights of dogs, the standard deviation can be quite large. All right, let's go to the next example here. Oops. Which of the distributions has a larger standard deviation? So what we are seeing here is a dot plot for each of the distributions. So we have the data values down here on the bottom, and then each dot represents one of those data values, right? So in the first data set, I see we have the numbers 38 occurs once, 39 3 times, then we have 40 occurring 4 times, a 42 and a 43. Right? So that's the set of data. Just think of it as those numbers, where the number of dots is the number of times that number occurs. So by looking at these two pictures, which one has a larger standard deviation? Well, which one's more spread out? Well, of course, the one on the right. Right? This guy has the larger standard deviation, because the values are spread all the way from 33 to 47, and they're spread pretty evenly throughout there. They're pretty well spread out. Whereas in the one on the left, the data values are all concentrated pretty closely around 40. Right? So the standard deviation is quite small. They don't really get much further away. They don't get very far from 40. So, yep, the one on the right has the larger standard deviation. Let's look at another example. Suppose Alan gets a score of 600 on his SAT, and Betty gets a score of 28 on her ACT. Who had the better score? Who should be more proud? Well, this depends, right? I mean, it depends on how how these scores work, right? I mean, they're different exams. So you can't say that a 600 is better than a 28, because 600 is an SAT, and the 28 is an ACT. They're different exams, so the numbers mean different things. So how do we measure this? Well, if you happen to know what the mean and standard deviation are for these different exams. So if we have data from everybody who took these exams, right? So everyone who takes this exam, we take the data and we compute a mean and we compute a standard deviation. Maybe we can use this to see how much these scores differ, right? So let's take a look at Alan's score of 600, right? Alan's score of 600 here. Let's see, on average, scores differed 100 from the mean, right? That's what the standard deviation is telling us. So he is exactly one standard deviation higher than the mean. So it's about how much scores differed from the mean on average, and he's about that much higher, right? So Alan's score is one standard deviation above the mean score, right? Take 500 plus 100, you get Alan's score. Now what about Betty? Well, the standard deviation for the ACT was 5, and Betty's score was 28. Okay, so how does her score relate in standard deviations? Well, if I add a standard deviation to the mean, I get 27. 28 is more than that. So Betty's score is more than one standard deviation above the mean. Is more than one standard deviation. So she did better than the average amount that people varied from the mean. So what we're doing here is we're comparing their scores to how people did overall on those exams. And that puts the score in the frame of reference of what that exam is about, which is what we want to do. So who would you say did better? Well, I would definitely say that Betty did better. Right? Betty did better on this exam because she is more standard deviations above the mean than Alan is. And so this is a good way to use standard deviations. Okay, there's one other thing I want to talk about, and that is variance. And this is super simple. Once we know standard deviations, variance is no big deal. Sorry, I can barely see anything because the sunlight is glaring through my window here. Okay, so let's talk about variance. So these formulas look pretty messy again, right? But if you think about it, they're not so bad. Once you know the formula for standard deviation, these are almost the same. What's the difference? The square root's gone. That's the only difference. These are exactly the same formulas that we saw before, but without the square root. All right? So population variance is just the square of the population standard deviation. And so therefore, we denote population variance by sigma squared. And you compute it by doing the same thing we did for standard deviation, but not including the square root. Because if you square the square root goes away. And the same thing for sample variance. Sample variance is just the square of the sample standard deviation. So to compute it, just do what you did for the sample standard deviation, just don't include the square root. And we denote it by s squared. Okay, so if we go back to that first example here, excuse me, I can't see the, okay, here we go. If we go back up here, and we wanted to compute the variances in these problems instead of the standard deviation, all we do is take these numbers and square them, right? So the variance here, let me do this in blue. Okay, the variance would be the same thing but without the square root. So the variance is just 2 over 4, or 0.5. Right? That's the variance. And if we go down here, what would the variance have been? Well, the variance will just be, so s squared would just be, instead of square root of 2/3, it would just be 2/3, right? Or if you wanted to write it as a decimal, 0.6667. It's good practice to round to 4 decimal places in this class. Okay, you'll want to do that on the homework. Sorry, you can't really see that. Here we go. Okay, 0.6667. So not too much more work to do variance, right? So that's it for today in this video. So I will see you in the next one.